There we go. All right. So what I do is a fairly when you start talking about it, it kind of sounds like a little niche thing, and it is a little niche thing, but there's more to it than it meets the eye. So what I've developed and with a bunch of other support, of course, is through wall communication stuff. And the problem statement shown here is you have a structure, a sealed structure, and you want to get information into or out of that sealed structure. Okay, and that sealed structure is dangerous in some way, or the outside or inside is dangerous in such a way. You're talking about pressure, vacuum, temperature, radiation, volatile chemicals, or explosives. To give you an idea, the initial project that was worked on for this was a nuclear containment vessel. So you're talking about pressure, temperature, and radiation effects in that application. So how do you get that sensor measurement outside of that structure? So mechanical penetrations are the first thing that would make sense. Can I push wires through that structure? And of course you can, but it doesn't make sense in a lot of applications. Mainly, getting that sensor information from inside or outside that vessel comes at a cost of decreased structural integrity, which makes that sensor measurement not worth it anymore because it compromises. Let's say, going back to the nuclear vessel, it compromises the integrity of that vessel. So you don't want to do something like that. And if you do something like that, it substantially increases the cost as you have to design the penetrations. Similarly, you might say, what about RF transmissions? Well, that doesn't work because most of these vessels are metallic, which produce Faraday shielding, so you can't transmit RF signals through it reliably. So what we work on is the ultrasonic alternative to that. So we take two transducers on either side of the wall and send vibrations through the wall to send both power and data. Some applications and some implementations are shown on this slide. So one of the ones that we are working on right now is the aircraft or spacecraft application. You can see a block diagram of this right here. And really, my portion of it really resides right here, the ultrasonic gateway. But there's other sensor and network applications being worked on in the larger group. Oil well applications. So you can see these are casings of an oil well, talking about the casings. This is also an oil well on the bottom right, talking past an obstruction in the oil well. And then some implementations. So the top middle here, that's a high rate communication system that was developed almost a decade ago, actually. But it's still a pretty good picture. An array of transducers that we might use. And then the blue one here is a more recent device that we've built up. What are these things capable of doing? So we can send power using these things, and some numbers that we've demonstrated, though these aren't limitations, are 50.1 watts through a carbon steel barrier. Actually, this barrier right here. 81 watts through a thinner barrier, 141 watts through this barrier on the right. And just to give you an idea of what something like this might look like, actually, I don't. I'm gonna skip that since I can't share a video through that. I did have a video I was going to show. There's also data capabilities. So we develop these things for different applications: low rate operation, medium rate operation, and high rate operation. Low rate might look like 100 bits per second to at most 10 kilobits per second. Medium rate, we're looking at like maybe 1 megabit per second. And then a high rate to 1 gigabit per second. And then, so what happens within this development? So it's highly multidisciplinary. You're looking at digital communication implementations, both digital and analog circuitry building, building the transceivers, building power transmission subsystems, integrating our sensors, and doing ultra low power design, which sounds tedious, but I love doing that one. I bolded this one, the microcontroller firmware development. So we do a lot of that in this because we're building the routines to operate all this stuff. PCB design and assembly. So this is really hands-on, actually doing circuit design, designing out the PCB and building the PCB. And transducer design and integration, so the mechanical portion of this, building using piezoelectric transducers. If you're interested in working with me, I don't have a lot of bandwidth for adding people, but I do like to add some undergraduates. I can do paid or credit, and I can do some master's work. Unfortunately, I don't have the funding to support PhD students, but I would love to be able to do that in the future on this. All right, that's what I had.